So this section just kind of finishes up this, it brings full circle this idea that colligative properties, like we talked about with freezing point depression and boiling point elevation, colligative properties actually depend on just the number of particles. So for instance, when we have something dissolve, when a salt dissolves, it breaks up into its cation and anion. We call that ionization. So you actually can get more bang for your buck with regard to particles. The cation is a particle and the anion is a particle. So I'll kind of show you what that means. So colligative properties again depend only upon amount, but not on on amount, not on what the solute is. Okay, so what does this look like? Well, first off, let's kind of talk about what electrolytes are. An electrolyte in general is a compound that if you dissolve it in water, it will conduct electricity. And of course, the reason it conducts electricity is because you have charged particles that have dissociated or ionized. So, for instance, if we have ethanol, does not conduct electricity. Why? Because there's no charged particles to facilitate the flow of electrons from this negative plate to this positive plate. So thus the little light's not lighting up. Well, what if we switch it up to KCl, potassium chloride? The thing about KCl is that it will ionize into K pluses and Cl minuses, and that's actually what you see here. And that does allow the flow of electricity from the negative plate to the positive plate. And it what we say completes the circuit, and so actually your light will light up. Then we have something that's kind of, I don't know if you tell the difference between these two, but this one is really bright and this one is a little bit dimmer. So notice what we've got going on here is we have fewer ions to help the transfer of electrons. And so what's the difference here? This caption says it's an acetic acid solution, which is not as strong of an electrolyte as HCl. To a certain degree, and we'll talk more about acetic acid as a weak acid, to a certain degree it does ionize, but not as much as KCl. So, like I said, you get more bang for your buck. So if you have just one of these splits apart, you get two particles for the price of one. Okay. Here, actually, check this out. The subscript 2, so calcium nitrate, we have 1 calcium and 2 nitrates. So here you get 3 particles, 2 particles. Okay. Notice that this is actually just showing the AQ means aqueous. I'm not sure. All right. This is showing you the ionization or the dissolving of potassium chloride. Okay, and again, remember that the water molecule has a partially negative oxygen and partially positive hydrogens. So you see them kind of, the partial negative oxygens surround the positive cation, and the partial positive hydrogens surround the negative anion. Kind of talked about that. So you might run into this sort of problem where we have these 1, 2, 3, 4. These four solids. AQ means we're going to go ahead and dissolve them in solution. And if you have a 0.1 molal solution of each, which one is going to have the greatest effect on raising the boiling point temperature? So, in other words, remember, boiling point elevation is a colligative property. So which one is going to give you the most particles? Okay. Well, let's take them one by one. So this is your, I think this is glucose. This is just sugar, dissolving sugar in water. Well, sugar is molecular, and you'd be like, I didn't know this is how it's going to work. Well, hopefully you know that when you dissolve it in water, it doesn't ionize. So in this case, you get one bang for your buck. So the effective molality is 0.1. Well, check this out. Okay, if we have 0.1 molal, and we have 0.1 molal of this, and 0.1 molal of this, notice the effective molal is 0.2, right? What about this one, calcium chloride? Of course, subscript 2 reminds us we have 2 chloride ions will be formed when this dissociates, just one, the calcium cation. So this is why we have 3 particles. Effective molality, 0.3. So this would, with the increased effective molality, this actually gives you 4 particles, 1 aluminum anion and 3 chloride anions. So 4 particles, effective molality of 0.4. So you would expect this one to have the greatest effect, that colligative effect, at elevating the boiling point temperature. And you'd be right. Okay, yep. So it will have the highest boiling point, the greatest boiling point elevation, and the lowest freezing point, the most extreme freezing point depression. The glucose, the sugar, will have the least, because it was just 1 particle that's not going to ionize. Least effect, I guess I should say. Yeah. Notice that this is a good point, that actually even the sugar, if we dissolve it in water, it still will have an effect on water of elevating the boiling point temperature and depressing the freezing point temperature. All right, so here's the deal though. If we get, as our concentrations become higher and higher, our ionization or dissociation might be more limited. So they will not totally separate concentrations. Keep that in mind. So I think I have, just keep that in mind. This again is showing you as concentration of dissolved ions increase, the ion-ion interactions are more likely. So here we have, this is more relatively concentrated solution of potassium chloride. And so you definitely have this sort of thing where you don't have the particles separated. That makes sense. I'm liking it. I like it's a good figure. So I'm building up to how do we quantitate this? How do we talk about getting more bang for your buck for the ionic compounds and factor in that you'll get so many more particles than just one. So it looks like this, and there won't be anything on your test about this to work any problems, but you should probably be familiar with this. The Van Hoff factor is the ratio of the moles of particles in the solution per or divided by the moles of formula units that ultimately dissolved. So, for instance, we could have HCl. You expect to get a Van Hoff factor of 2, and you got a measured effective mole concentration of 1.9. And again, the more concentrated it is, the more your measured Van Hoff factor will differ from that predicted. Here we have magnesium sulfate. Okay. Magnesium chloride, we expect 3, 2.7. Iron 3 chloride, you expect 4, 3.4. Glucose, again, you expect 1. So this is showing you with the decreased decreased molality that you can get closer to what you expect. So for instance, we expect 2, 2, and 3 here. So let's see how we do. Not so good, getting better, getting better, getting better. Okay, so there you go.